Tonight, we're going to confront a number that shouldn't make sense. The universe is 13.8 billion years old. So light has only had 13.8 billion years to travel. And yet, when astronomers look out in every direction, the most distant things they can see are now sitting almost 46 billion light years away. Not 13.8, 46. How can we possibly see something farther away than light could have traveled since time began? And here's the part that's even stranger. Most of what we can see tonight, we could never reach. Not with a signal, not with a ship, not ever. The light arrives, but the door has already closed. It's one of the deepest truths in all of cosmology. Before we go any further, if these journeys through the cosmos are the kind of thing you enjoy, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that feels almost too obvious to say out loud. Light takes time to travel. It is fast, unimaginably fast, but it is not infinitely fast. And because it takes time to cross distance, everything you have ever seen with your eyes is in some tiny way a message from the past. The page in front of you, the wall across the room, the face of someone you love, you are seeing all of it as it was a few billionths of a second ago. On human scales, that delay is so small, it may as well not exist. But stretch the distances out, and the delay stops being a technicality. It becomes the single most important fact about how we see the cosmos. Now hold that thought and look upward. When you look at the moon, you are seeing it as it was a little over 1 second ago. When you look at the sun, you are seeing light that left its surface more than 8 minutes in the past. Look past the sun to the nearest other star, and you are looking back more than 4 years. And here is where the idea starts to open up into something enormous. Because if you keep going past the neighboring stars, past the far edge of our galaxy, past other galaxies entirely, the light reaching you tonight has been traveling for so long that it left its source before the Earth existed, before the sun existed, before almost anything you could name existed. You're not just looking across space, you're looking down a corridor of time so long that it reaches nearly to the beginning. This is what astronomers are pointing at when they use the phrase, the observable universe. It sounds like it should mean the part of the universe we happen to have looked at so far, or the part our telescopes are good enough to reach. But that is not what it means at all. The observable universe is the region from which light, or any other kind of information, has had enough time to reach us since the cosmos first became transparent. It is defined by a speed limit and a clock. The speed limit is the speed of light. The clock is the age of the universe. And together they carve out a sphere around us, a bubble of everything whose light could possibly have arrived by now. Anything beyond that bubble is not hidden because it is faint or because our instruments are weak. It is hidden because its light is still on its way and simply has not gotten here yet. That distinction matters more than almost anything else we will talk about tonight. So let me press on it. The edge of the observable universe is not a place. It is not a wall. There is no shimmering barrier out there, no shell of matter, no line painted across the dark. If you could somehow travel to what we currently call the edge, you would not find nothing on the other side. You would find more galaxies, more stars, more of the same kind of universe you already know. And those galaxies would have their own observable universe, their own bubble of arrived light centered on them. The edge only exists relative to an observer and relative to a moment in time. Move the observer and the edge moves with them. Wait a while and the edge grows because more distant light keeps arriving with every passing year. This is also why it is a mistake to imagine that we sit at the center of the universe in any special, privileged way. We do sit at the center of our observable universe, but only in the trivial sense that a swimmer at sea sits at the center of their own circle of horizon. Every swimmer sees themselves ringed by the same distance of horizon in all directions. That does not make any one of them the center of the ocean. It just means the horizon is a property of where you are standing and how far you can see. A civilization in a galaxy billions of light years away would look out and find themselves apparently at the center of their own perfectly round bubble, with the farthest light arriving equally from every direction. They would be just as centered and just as unspecial as we are. The centering is about the observer, not about the cosmos having a middle. So the observable universe is our bubble of arrived information. But how big is that bubble? Here is where we run straight into a contradiction that has puzzled people the first time they hear it. And it is worth savoring rather than rushing past. The universe is about 13.8 billion years old. Light has been traveling toward us for, at most, that long. So a reasonable person would guess that we can see out to a distance of 13.8 billion light years, and that the whole observable universe is therefore about 27.6 billion light years across. That guess is completely sensible. It is also completely wrong. The real figure that cosmologists quote is that the most distant regions we can observe are now roughly 46 billion light years away in every direction, making the observable universe about 93 billion light years across. Read that again, because it should bother you. The light has only been traveling for 13.8 billion years. Nothing outraced it. Nothing cheated the speed limit. And yet the source of that light is now sitting 46 billion light years away. More than 3 times farther than the light could have traveled if space had simply stayed still. How is that possible? How can we be seeing something whose present distance is larger than the total distance light could have covered since time began? The answer is the single most important idea in this entire story, and it is this. Space itself has been expanding the whole time that ancient light was on its way to us. The light did not travel across a fixed, frozen distance like a runner crossing a track of fixed length. It traveled across a track that was stretching underneath it as it ran. Picture a beam of light that set out billions of years ago from some distant patch of matter. When it began its journey, that patch was relatively close to the region that would one day become us. But as the light crawled toward us at its fixed, unchanging speed, the space between the source and us kept growing. Every stretch of distance the light had already covered got longer behind it, and new distance kept opening up ahead. By the time the light finally arrived tonight, the patch it came from had been carried far, far away by that ongoing expansion, much farther than the length of the path the light actually traced. This is the resolution to the paradox, and once you see it, the strangeness turns into elegance. There is no rule that says the present distance to a galaxy has to be smaller than the distance its light traveled. The distance the light traveled is one thing. The distance to the galaxy right now is another thing entirely, because the whole stage has been swelling in the meantime. The light travel distance and the present day distance are simply not the same number. and in an expanding universe they can differ enormously. The light from the most ancient sources traveled for something like 13 billion years. But the sources themselves have since been swept out to more than 46 billion light years away. Astronomers have careful language for pulling these ideas apart, and while I do not want to bury you in terminology, the distinctions are worth having in plain words. The first idea is look-back time. That is simply how long the light has been traveling. How far into the past you're peering when you catch it. When we say we see a galaxy at a look-back time of 10 billion years, we mean the light left it 10 billion years ago, and we are seeing it as it was then, not as it is now. The second idea is light travel distance. The distance you would get if you naively multiplied that travel time by the speed of light. It is a real distance in one sense, but it is a slippery one, because it does not correspond to where the object is at any single moment. It is more like the odometer reading on the light's journey. The third idea is the one that produces those giant numbers, proper distance, sometimes called present-day distance. This is the distance to the object right now in this cosmic instant. If you could somehow freeze the expansion and lay a cosmic ruler between us and it. Proper distance is what cosmologists mean when they say a galaxy is 46 billion light years away. They are not saying its light took 46 billion years to arrive. It could not have in a universe younger than that. They are saying that if you stop the clock right now, the gap between us and that galaxy would measure 46 billion light years, because expansion has stretched the original modest gap into something vast. And there is a fourth idea, co-moving distance, which is a clever bookkeeping trick. It factors the expansion out entirely, giving every galaxy a fixed label that does not change as space grows. Co-moving distance is how astronomers keep track of who is who without the numbers sliding around every year. For our purposes, the crucial pair to keep straight is the odometer reading of the light versus the true present-day gap. The light travel distance versus the proper distance. One is 13-ish billion, the other is 46-ish billion. Both describe the same galaxy. Both are correct. They just answer different questions. I want to make sure this lands. So let me put it in a homelier image. Imagine you mail a letter to a friend, and the moment you drop it in the post box, your friend begins walking away from you at a steady pace. The letter is fast. It moves toward wherever your friend currently is. But your friend keeps moving, so the letter has to keep chasing a receding target. When the letter finally arrives, your friend is much farther from the post box than they were when you sent it. Now, the distance the letter physically traveled is one number. The distance your friend now stands from the original post box is a larger number. Nobody broke any rules. The letter never moved faster than letters can move. It is just that the destination kept retreating during the delivery. The expanding universe is like that. Except, it is not your friend walking away through fixed space. It is the very ground between you and your friend that keeps stretching, adding distance everywhere at once. That is why the galaxies whose light we catch tonight are now so absurdly far away. And this is why you must never, ever say that the universe is only 13.8 billion light years across. That statement smuggles in the assumption that space stayed frozen while light crossed it, and space did no such thing. The age of the universe sets how long light has traveled. It does not set how far away the sources have ended up, because the sources have been riding an expanding tide the entire time. The 93 billion light-year figure is not a contradiction of the 13.8 billion year age. It is a direct consequence of it, once you remember that the stage has been growing. There is one more subtlety hiding in that 93 billion figure, and honest cosmology requires me to flag it rather than gloss over it. That number is not something we stretched a tape measure across. It is the output of a model, our best, well-tested model of how the universe has expanded over its history, built from an enormous body of observations. We measure the light. We measure how much that light has been stretched, how far its colors have been dragged toward the red. And then we use the expansion history encoded in the model to translate that into a present-day distance. So when you hear 93 billion light-years across, understand that it is a robust, carefully derived figure, but a model-dependent one. It describes the present separation between extremely distant regions according to our cosmological framework, not a distance any beam of light has actually traversed along a static path. The framework has been checked against so many independent lines of evidence that we take the figure seriously. But it is an inference about the present, drawn from ancient light, not a direct sighting of the present. That honesty will matter a great deal later, when we start asking not just what we can see, but what we could ever touch. Let me pull back now and rebuild the scale from the ground up, because these numbers only mean something if you can feel your way out to them step by step. Start where you are, on the Earth. The Earth is a rocky ball about 8,000 miles across, and from where you sit, it is the whole world. Continents, oceans, everything anyone has ever done. But light crosses that entire world in a small fraction of a single second. On the scale we are building toward, the Earth is not even a rounding error. It is the first, smallest rung on a ladder that is about to climb almost past comprehension. Take one step out to the solar system. Now distances stop being measured in miles and start being measured in how long light takes to cross them. Light leaves the sun and reaches us in about 8 minutes and 20 seconds. It takes light more than 5 hours to crawl out to the orbit of distant, icy Pluto. The whole planetary system, from the sun to the outer worlds, is a region that light needs the better part of a day to traverse. Already the Earth has shrunk to a speck, and yet the solar system, this thing so large that our fastest spacecraft take years to cross it, is itself about to vanish, because the next rung is not measured in light hours. It is measured in light years. The nearest star beyond our own is a little more than 4 light years away. Say that slowly. The light entering your eye from that star tonight left it more than 4 years ago, back when you were 4 years younger, doing whatever you were doing then. It crossed a gulf so wide that our swiftest probes, moving faster than any human has ever moved, would need tens of thousands of years to reach it. And that is the closest neighbor. Fan out from there, and the local stars you can see on a dark night are scattered across tens and hundreds of light years. The bright red shoulder star of the hunter in the winter sky. Betelgeuse sits several hundred light years away. Its light older than the telescope, older than the printing press. Every point of light in your night sky is a message that's set out years, centuries, or millennia ago. Take another step, and all of those stars, every single one you have ever seen with the naked eye, collapse into a single structure, our galaxy, the Milky Way. It is a vast spiral wheel of a few 100 billion stars, and it is about 100,000 light years across. Light, that impossibly fast messenger that crossed the Earth in an instant, needs 100,000 years just to travel from one edge of our galaxy to the other. Our sun is buried in one of the spiral arms, roughly 26,000 light years out from the center, an ordinary star among hundreds of billions. On this rung, the Earth is not merely invisible, it is inconceivable. The entire solar system is a single unremarkable point somewhere along one arm of a wheel so large that light spends 1,000 human lifetimes crossing it. And here's the thing about that step that I do not want you to skate over. Because most people, when they first learn how big the galaxy is, quietly assume the galaxy is more or less the universe. For most of human history, that assumption was the frontier of knowledge. The band of milky light across the night sky was the edge of everything anyone could conceive. But the Milky Way is not the universe. It is one wheel among an ocean of wheels, and the very next rung of the ladder takes us clean out of it, into a distance so much larger that the 100,000 light-year span of the galaxy becomes, itself, a speck. Step out from the Milky Way then, and the first thing you meet is not empty darkness, but company. Our galaxy has neighbors. A small huddle of galaxies traveling together through space, held loosely near one another. The nearest large one, the great spiral called Andromeda, lies about 2.5 million light-years away. Hear that number against the one we just used? The galaxy is 100,000 light-years across, and the nearest big neighbor is 2.5 million light-years off. 25 galaxy widths of empty space between us and it. The light arriving from Andromeda tonight left it 2.5 million years ago, when creatures we would just barely recognize as our ancestors were walking the Earth. That light is older than our species, and Andromeda, along with our Milky Way and a few dozen smaller galaxies, forms our little neighborhood, a modest gathering scattered across several million light years. That gathering is the next rung, and already the entire Milky Way, that wheel too vast for light to cross in 1,000 lifetimes, is just one member of a small local cluster of them. Keep climbing, because the rungs do not stop and each one dwarfs the last. Beyond our little group of galaxies lie richer, denser collections. Great clusters where hundreds or even thousands of galaxies swarm together, bound near one another, stretching across tens of millions of light years. Our neighborhood is drawn toward one such vast concentration, part of a larger association of clusters spanning 100 million light years and more. And even these enormous clusters are not the top of the ladder. Zoom out further still, and a pattern emerges across the entire sky. The grandest architecture there is. The galaxies are not scattered at random through the dark. They are strung together into immense threads and sheets. Luminous filaments of thousands upon thousands of galaxies, woven around colossal, near-empty voids where almost nothing shines at all. This is the cosmic web, a spidery, foam-like structure of glowing strands and dark hollows, stretching across hundreds of millions and then billions of light years. Our Milky Way, our whole local group, our nearby clusters, all of it is a single bright knot on one strand of that web. So walk the ladder in your mind, one last time, and feel each rung fall away beneath the next. Earth. A speck light crosses in an instant. The solar system, a region light needs a day to span. The nearest stars, years away. The Milky Way, 100,000 light years across. Our whole galaxy. The local group of galaxies, millions of light years. With the Milky Way just one member. The nearby clusters, tens of millions of light years. Our group, just one part. The cosmic web. Billions of light years of glowing filament and dark void, our cluster's just one knot upon it. And beyond the farthest strands we can see, the particle horizon itself, 46 billion light years out, where the oldest light of all is only now arriving. At every single rung, everything from the rung before has shrunk to nothing. And nowhere on that entire ladder is there a wall, an edge, a place where things stop. There is only structure and more structure, fading out to the limit not of space, but of how far light has had time to travel. I want to leave you for now, holding both ends of the paradox at once, because that tension is the true subject of everything that follows. Here is the tension. The observable universe is a sphere of arrived light, centered on us the way a horizon is centered on a swimmer, not because we are special, but because that is simply where we happen to be looking from. It reaches out to a present-day distance of roughly 46 billion light years. A bubble about 93 billion light years across, even though the universe has existed for only 13.8 billion years. And it reaches that far precisely because space expanded while the light was in transit, dragging the ancient sources far beyond the simple distance their light traveled. The observable universe is not the whole universe. The whole universe extends beyond our horizon, possibly by a vast amount, possibly without any edge at all. Spatially infinite for all we can directly determine. We cannot see past our bubble, so we cannot measure where or whether the real universe stops. What lies beyond is almost certainly more of the same. More galaxies, more stars, more cosmic web, obeying the same laws we see at home. But that is an inference, a reasonable extrapolation from everything inside our horizon, not something we have laid eyes on. So we are left with a first, strange truth to carry forward. The number that describes the size of what we can see, 46 billion light years to the edge, 93 across, is genuinely enormous, far larger than the age of the universe would naively allow, and it is growing every year as more distant light finishes its long journey in. You might think that means the reachable universe, the part we could someday touch or talk to, must be growing too. That the more we can see, the more we can hope to visit or signal. It feels natural. It feels obvious. It is also, as we are about to discover, almost exactly backwards. Because the very expansion that made our observable universe so gloriously, paradoxically large is the same expansion that is quietly closing doors all across the sky, carrying most of those visible galaxies beyond any signal we could ever send. Even as their ancient light keeps pouring in, we can see them. We are watching them right now, and most of them we can never reach. To understand how that can be true, how a galaxy can be blazing in our telescopes tonight, and yet lie permanently outside our future reach, we first have to go all the way back to the oldest light there is, the faint afterglow of the young cosmos itself, and ask what it can and cannot tell us. Because that ancient glow marks not the edge of space, and not the beginning of time, but something subtler and stranger. The moment the universe first became clear enough to see through at all. A moment ago, I promised to travel back to the oldest light there is, so let us go there now. But first, a warning about what that light is not. It is not the flash of the Big Bang. It is not a photograph of the beginning of time. It is not a picture of an edge where space stops. It is something quieter and, once you understand it, far stranger than any of those things. It is the moment the universe stopped being fog and became glass. To see why that moment exists at all, and why it forms a kind of horizon in time rather than in space, we have to understand what the early universe was actually like. Not as an explosion in the dark, but as a searing, glowing, opaque fluid that filled everything, everywhere, all at once. Rewind the expansion. Run the cosmic film backward, and everything that is now spread thin and cold gets squeezed closer and grows hotter. Galaxies dissolve back into scattered gas. That gas grows denser and more furious. Push far enough back and you reach a time, a few 100,000 years after the beginning, when the entire universe was filled with a plasma so hot that ordinary atoms could not hold together. An atom is a nucleus with electrons bound around it. But at these temperatures, the electrons were torn free, ripped away from their nuclei, and the cosmos was a churning sea of bare nuclei and loose electrons. This matters enormously for the story of light, because free electrons are ferocious at scattering light. A loose electron will grab a passing beam of light and fling it off in a random direction almost the instant it appears. In a universe packed wall to wall with free electrons, light could not travel in a straight line for any meaningful distance. It was absorbed and re-emitted, deflected and scattered, bounced around endlessly like sunlight trapped inside a thick fog. The early universe was quite literally opaque. It glowed, but you could not see through it, any more than you can see through the glowing interior of a cloud or the body of the sun. And I want to linger inside that fog for a moment, because it is easy to say the word opaque and move on without feeling what it truly means. Imagine you could somehow have been there, floating in the young universe as it was in that plasma era. You would not have been in darkness. Quite the opposite. You would have been drowning in light, blinding light, coming at you from every direction at once, a uniform furnace glow with no shape, no source, no depth, because every scrap of light was being scattered 1,000 times before it could travel any distance at all. You could not have seen your own hand held in front of your face, not because there was too little light, but because there was too much of it, coming from everywhere, carrying no image. Light in that era was like sound in a shouting crowd, present in overwhelming abundance, but incapable of carrying a clear message from any one place to any other. That is what opacity means for the cosmos. Not black, blinding, formless, and informationless. A glowing wall you cannot see into, because the seeing itself is scrambled. Now, why exactly is it the free electrons that do this? And why does binding them into atoms change everything? This is worth understanding precisely, because it is the whole mechanism behind why the earliest universe is hidden from ordinary light. And it is not merely a matter of the plasma being thick. A free electron, one that is not attached to any nucleus, roaming loose through the hot soup, is exquisitely good at intercepting light. Light is an electromagnetic wave, a rippling of electric and magnetic fields, and a free electron, being a bare electric charge with nothing to anchor it, feels that rippling field and is set jiggling by it, and a jiggling charge promptly radiates the light back out in some new direction. So a free electron acts like a tiny, ever-present mirror, scattered a countless number of times through every cubic inch of space, catching each beam and hurling it off course. With free electrons everywhere, no beam of light survives more than the shortest hop before being knocked aside. That is the fog. But bind that same electron into an atom, let a nucleus capture it, so that it is no longer free but held in place around the nucleus in a specific quantized arrangement, and its relationship to light changes completely. A bound electron cannot simply jiggle in response to any passing wave and fling it back. It can only absorb light of very particular energies, the specific amounts that would kick it from one allowed arrangement to another. Light of any other energy sails straight past it, untouched, as though the atom were not there. And most of the light streaming through the young universe didn't have those special energies. So, the instant the electrons were captured into atoms, the overwhelming majority of the light found itself passing through matter that had suddenly stopped interacting with it. The mirrors were gone. The fog was not so much blown away as switched off. The very same particles that had been scattering light everywhere were now bound into atoms, ignoring it almost entirely. That is the physical heart of why the universe became transparent, and why everything before that instant is sealed behind a wall that ordinary light can never cross. Before it, light was trapped by free charges. After it, light flew free through neutral atoms. And this plasma era, hot as it was not even the deepest layer of hiddenness. Go further back, squeeze harder, and you pass through stranger and more extreme conditions still. An era so hot and dense that atomic nuclei themselves were being forged in the first few minutes. And before that, epochs of energy so ferocious that the familiar particles of matter had not yet settled into the forms we know. Each of these earlier stages is buried behind the one in front of it, and all of them are buried behind the fog, sealed off from any ordinary light we could ever collect. The plasma wall is simply the last and outermost of a series of veils, the one nearest to us in time, and therefore the one we run into first when we try to look backward with light. Everything behind it recedes into a past that ordinary light was never able to escape. Then the expansion did its patient work. As space stretched, the plasma thinned and cooled, and when the universe was roughly 380,000 years old, it crossed a threshold. It became cool enough, down to a few thousand degrees, that the bare nuclei could finally capture the free electrons and hold onto them, forming complete neutral atoms of hydrogen and helium for the first time. And the instant the electrons were bound up inside atoms, they stopped being free to scatter light. The fog lifted. All at once, across the entire cosmos, light that had been trapped and bouncing for hundreds of thousands of years was suddenly free to fly in a straight line. The universe became transparent, and that light, released at the moment of transparency, streaming outward ever since, is still arriving today. We call it the cosmic microwave background, and it is the oldest electromagnetic light we can directly observe. I need you to hold on to exactly what that light represents, because it is so easy to get wrong. The cosmic microwave background was not emitted at the instant of the Big Bang. It was emitted 380,000 years later, at the moment the fog cleared. It does not mark the beginning of time, and it does not mark the location of the beginning. It marks the moment the universe first became see-through. When you detect this ancient light, you're not looking at the birth of the cosmos. You're looking at the earliest instant that light was able to travel freely. The surface of the fog, so to speak. The last place the light was scattered before it broke loose and came to us. Astronomers sometimes call it the surface of last scattering, which is a beautifully literal name. It is the wall of the fog, and beyond that wall, going further back in time, ordinary light simply cannot show us anything, because there, the universe was opaque. Now here is a point that trips up almost everyone, so let me be careful with it. When I say this light comes from the surface of last scattering, it sounds like it comes from a particular place, a shell out at the edge of things. But that fog filled the entire universe, including the very region that would one day become you and the ground beneath your feet. The plasma was everywhere. So the cosmic microwave background is not arriving from one direction, from some distant wall off to the side. It is arriving from every direction at once, uniformly, filling the whole sky. The reason we see it as a shell far away is subtle, and it is the same effect we met at the very beginning of our journey. We are not seeing the fog as it is now. The matter that made that fog is now the galaxies and stars around us, long since cooled and clumped. We are seeing light that left the fog 380,000 years after the beginning, and that light has been traveling toward us for the entire age of the universe since. So the light we catch tonight comes from the fog as it existed in a thin shell at just the right distance that its light is only now completing the trip. Look in any direction and there is such a shell, because in every direction there was fog, and in every direction the light from the fog at exactly the right distance is arriving right now. It is not a wall around the universe, it is the edge of what ordinary light can reveal about the past, and it surrounds us because the early hot state was everywhere. There is a further wonder hiding in this ancient light, one worth pausing on, because it is not merely a featureless glow. When we map the cosmic microwave background across the whole sky with sensitive instruments, we find it is almost perfectly smooth, the same temperature in every direction to an extraordinary degree, but not quite. There are faint ripples in it, patches very slightly warmer and very slightly cooler than average, differences of a tiny fraction of a degree. And those minuscule ripples are among the most precious data in all of science, because they are a snapshot of the seeds of everything. The slightly denser patches in that ancient fog were the regions where gravity would, over the following billions of years, pull matter together into the first stars, the first galaxies, the great filaments of the cosmic web. When you look at a map of those temperature ripples, you are looking at the blueprint of the large-scale structure of the universe, drawn when the cosmos was 380,000 years old. Every galaxy that exists, including our own, grew from one of those faint, warm or cool spots. The oldest light we can see is not just old, it is the baby picture from which the entire visible universe developed. The light itself has been transformed almost beyond recognition on its long journey. When it was released, it was the fierce glow of matter at a few thousand degrees, visible light and infrared, the color of a dull red-hot ember or hotter. But it has been traveling through expanding space for 13.8 billion years, and that expansion has stretched it. As space grew, the waves of that light were stretched along with it, dragged out to longer and longer wavelengths. Their color pulled far past red, past infrared, all the way down into microwaves. The temperature we associate with it has dropped correspondingly, from thousands of degrees down to a whisper, just under 3 degrees above absolute cold, a bare 2.7 degrees on the absolute scale. This is the same stretching, the same reddening that we will keep meeting throughout this story. The universe expands, light riding through it gets stretched, its color shifts toward the red, and its energy drops. The cosmic microwave background is the most extreme everyday example of this we have. An ember's glow stretched by cosmic expansion into a faint hiss of microwaves that bathes the entire sky, arriving equally from everywhere, the cooled and reddened relic of the moment the fog first cleared. In fact, A tiny fraction of the static you might once have seen on an untuned analog television was this very light. The actual afterglow of the young cosmos, caught by an ordinary antenna. You have very likely, without knowing it, already met the oldest light in the universe. So that is the wall in time that ordinary light cannot cross. Everything earlier than 380,000 years, the plasma era, and everything before it, back toward the first fraction of a second, is hidden from us behind the fog. Not because it is far away in the sideways sense, but because light could not escape it to carry us the news. No matter how powerful a telescope we build, no matter how sensitive our instruments, we will never take an ordinary light photograph of the universe from before it became transparent, because there was no free light to take a photograph with. This is a horizon of a different kind than the one we discussed before. It is not a horizon of distance set by the finite age of the universe. It is a horizon of opacity set by the physics of hot plasma. The observable universe in visible light ends, going backward in time at the surface of last scattering. Behind that surface lies a region of the past that ordinary light will always keep secret. And notice what a strange and specific kind of limit this is, because it teaches us something about the word observable that we will need again and again. When we speak of the observable universe, we very nearly always mean the universe observable in light. In electromagnetic radiation of one kind or another, from radio waves to visible light to the most energetic rays. Almost everything we know about the cosmos, from the nearest planet to the farthest galaxy, has come to us on that single kind of messenger. Light is the workhorse of astronomy. It is very nearly the whole of it. But light has this one profound limitation. It cannot carry us any news from before the fog cleared. Our entire electromagnetic window onto the past slams shut at the surface of last scattering. If light were our only possible messenger, then the first 380,000 years of cosmic history, the plasma era, the forging of the first nuclei, the wild early instants, would be sealed away forever, absolutely and permanently beyond any observation. The cosmic microwave background would be quite literally the oldest thing it is possible to see. Does that mean the earlier universe is forever unknowable? Not necessarily. And here I want to be careful to describe possibility without promising a result. Light is not the only messenger the universe has. There are, in principle, two other kinds of signal that could carry information out from before the fog cleared, because neither of them cares about free electrons the way light does. The first is the neutrino. Neutrinos are ghostly particles that barely interact with anything at all. They stream through solid matter, through planets, through you, in unimaginable numbers without so much as a flicker. Trillions of them are passing through your body every second as you listen to this, and not one in a lifetime will touch you. This near total indifference to matter is what makes them such extraordinary potential witnesses to the deep past. Because they interact so weakly, neutrinos decoupled from the cosmic soup even earlier than light did. They broke free while the universe was much younger and hotter than the moment of last scattering. A mere second or so after the beginning, when light was still hopelessly trapped in the fog. If we could ever detect this ancient neutrino background directly, it would carry a picture of the universe from a time long before the cosmic microwave background was released. From an era light itself can never show us, peeling back one of those deeper veils we spoke of. The catch, and it is a cruel one, is that the very property that lets neutrinos escape the early fog, their reluctance to interact, is exactly what makes them fiendishly hard to catch now. To detect a particle, something has to interact with it, and neutrinos almost never do. We can, with enormous and painstaking effort, detect energetic neutrinos from the sun and from certain violent events. But the primordial neutrino sea from the first second of the universe is far colder and far fainter, and catching it directly is an extraordinary challenge that lies beyond anything we can currently do. I want to be honest that it is a hope and a frontier, not a thing already accomplished. The second possible messenger is even more exotic: gravitational waves. These are ripples in the fabric of space itself, not a wave traveling through space, but a wave of space, a stretching and squeezing of distance that propagates outward from violent events. And here is what makes them so tantalizing for our purposes. There is no such thing as a substance that is opaque to a gravitational wave. Matter that stops light cold, the dense plasma, the fog of free electrons, is utterly transparent to these ripples in space. They pass through everything undisturbed, because they are not something moving through the stuff of the universe. They are a trembling of the stage itself. If violent processes in the earliest moments of the cosmos generated such ripples, and our best theories of those first instants suggest they very well might have, then those primordial gravitational waves could still be washing over us today, having passed straight through the fog as though it were not there, carrying information from the first tiny fractions of a second, from far behind every veil, from an era otherwise absolutely and permanently sealed off. In recent years, we have, for the first time, begun to detect gravitational waves at all, the ripples from dramatic events like the collision of black holes far out in the universe. And that was a genuine triumph. A whole new sense opening up after millennia of studying the cosmos with light alone. But detecting the faint primordial background of gravitational waves left over from the birth of the universe is a vastly harder task than catching the sharp ring of two colliding black holes, and it has not been done. So again, and I say it deliberately, these are avenues that could, someday, let us peer behind the wall of last scattering in ways ordinary light never can. They are real reasons not to declare the early universe permanently unknowable, but they are open possibilities at the very edge of what is achievable, not guarantees, and honest cosmology holds them exactly there. As promising doors, not as rooms already entered. Notice then that we have quietly widened what observable might one day mean. For all of history, it has meant seeable in light. But the universe speaks, at least in principle, in more than one voice. It speaks in light, which reaches us richly, but only back to the fog. It may speak in neutrinos, which slipped free far earlier, and it may speak in gravitational waves, which no fog can silence at all. The story of what is observable is not finished. It is still being written, as we learn to listen with senses other than sight. But for now, and for everything that follows tonight, light remains our overwhelming source of knowledge, and the wall of last scattering remains the practical edge of the visible past. Now let us step back and organize what we have. We have met so far two different kinds of limit on what we can see. One is the limit set by time and the finite speed of light. The fact that light from sufficiently distant regions has not had time to reach us yet. The other is the limit set by opacity. The fact that before the fog cleared, ordinary light could not travel at all. Both of these are horizons in a loose sense, boundaries on our knowledge. But the word horizon gets used in cosmology for something more precise. And if we are going to understand why most of the visible universe lies beyond our reach, we have to define our horizons carefully, because there are two very different ones, and they're constantly confused with each other. Getting them straight is the whole game. The first is called the particle horizon. This is the one we have essentially been describing all along. The particle horizon marks the greatest distance from which light or any information has had time to reach us so far, over the entire history of the universe, up to this moment. It is, in effect, the boundary of the observable universe, the edge of our bubble of arrived light. Everything inside the particle horizon is something whose signal has had enough time to get here. Everything outside it is something whose signal is still on the way and has not yet arrived. The particle horizon is about the past and the present. It answers the question, how far out into the universe can we possibly have received news from, given how long the universe has existed? And crucially, the particle horizon grows with time. Every year, light that has been traveling a little longer finally completes its journey, and the boundary of what we can see creeps outward. New regions, previously beyond our horizon, come into view. In that sense, the observable universe is expanding into our awareness, not just because space is growing, but because more distant light keeps arriving. The particle horizon today sits at that proper distance we keep returning to, roughly 46 billion light years, and tomorrow it will sit very slightly farther out. The second horizon is a completely different animal, and it points in the opposite direction, into the future rather than the past. It is called the cosmic event horizon. The event horizon does not ask, how far away is the most distant thing whose light has reached us? It asks something much more unsettling. If we send out a signal right now, today, at the speed of light, how far can that signal ever get? What is the most distant region we could ever hope to influence, to reach, to communicate with, starting from this moment? The particle horizon is about what can reach us. The event horizon is about what we can reach. And in an expanding universe, especially one whose expansion is speeding up, as ours is, these two boundaries are not the same. And the gap between them is the source of the entire heartbreak this episode is building toward. Let me make the difference vivid before we go further, because this is the hinge of everything. Imagine you shout into the dark. The particle horizon is like asking, from how far away could a shout have reached my ears by now? It depends on how long the world has existed and how fast sound travels toward you. The event horizon is like asking, if I shout right now, how far away is the farthest person who could ever possibly hear me? It depends on how the distances between us and everyone else are changing into the future. In a still, unchanging world, these two questions would have symmetric answers. But in a world where everyone is drifting apart and drifting apart faster and faster, the answers come apart dramatically. There can be people close enough that their old shouts reached you long ago. You can hear them clearly, and yet far enough and receding fast enough that a shout you send now will never ever catch up to them. You can hear them. They can hear your past, but your present can never reach them again. That, in a sentence, is the situation we find ourselves in with most of the galaxies in our sky. Hold that thought, because it deserves its own full treatment, and we will give it one. For now, I just want the two horizons cleanly separated in your mind. The particle horizon is the edge of what we can see, the reach of arrived light, growing outward year by year. The cosmic event horizon is the edge of what we could affect. the limit on how far any signal we send today can ever travel, a limit imposed by accelerating expansion. They are not the same boundary. They are not even the same kind of boundary. One looks backward and inward, gathering the light of the past. One looks forward and outward and marks the doors that are closing. Confuse them, and none of what follows will make sense. Keep them straight, and the deepest truth of our cosmic situation snaps into focus. There is one more thing I must insist on before we move outward again, and it is the same insistence I made about the cosmic microwave background, because the temptation to imagine a wall is so powerful. Neither of these horizons is a physical barrier. Neither is a surface you could touch or crash into. The particle horizon is not a shell of matter at the edge of the observable universe. It is just the distance beyond which light has not yet had time to arrive. And if you travelled out toward it, it would keep receding. And you would find ordinary galaxies the whole way, each with its own horizon around it. The event horizon is likewise not a wall in space. It is a statement about which regions the expansion has placed beyond the future reach of our signals. If you could ride alongside a beam of light heading toward the cosmic event horizon, you would not smack into anything. You would simply find that the destination keeps outrunning you forever. The horizons exist because of limited time and expanding space, because of the interplay of the clock and the stretching stage, not because space stops or because something solid stands in the way. There is no edge of the world out there. There is only the reach of light, in from the past and out toward the future, drawn against a background that will not hold still. And that refusal of space to hold still is exactly what we must confront next, in its most shocking form, because we have been speaking of galaxies as if they simply sit at various distances while their light travels to us. But the truth is far wilder. The most distant galaxies we can see are not sitting still. They are rushing away from us, and many of them are rushing away faster than the speed of light. That sentence should stop you cold, because you have been told your whole life that nothing can travel faster than light. And nothing can move through space faster than light. But space itself is under no such obligation. The distance between us and a faraway galaxy can grow faster than light can cross it. Not because the galaxy is speeding through space, but because fresh space keeps opening up along the entire line between us. And summed across billions of light years, that steady swelling builds into a rate of separation that outpaces light itself. This does not break the law that has anchored physics for over a century. It obeys it, and understanding exactly how it obeys it, how a galaxy can recede faster than light without any law being broken, and how, astonishingly, light from some of those very galaxies can still reach us anyway, is the key that finally unlocks why so much of what we see tonight is something we can never, ever touch. That is where we turn next, to the strange, misunderstood boundary called the Hubble sphere, and to the reason it is not the wall it first appears to be. Let me hand you now the sentence that breaks people's brains, and then spend the next while unbreaking them. Right now, tonight, there are galaxies visible in our telescopes that are moving away from us faster than the speed of light. Their light is arriving. We can photograph them, measure them, study them, and yet the distance between us and them is growing faster than light can travel. Both things are true at the same time. If that sounds like it must violate the most famous rule in all of physics, nothing can go faster than light, then good. That reaction means you have been paying attention your whole life. Now let me show you why the rule is safe, why nothing is being broken, and why the universe is even stranger and more elegant than the paradox first suggests. Start with the rule itself, stated precisely, because the precision is where the resolution hides. Einstein's special relativity says that nothing can move through space faster than light. An object cannot travel from one point to a nearby point across the local space between them, at a speed exceeding the speed of light. This is ironclad, tested countless times, woven into the deepest structure of physics. A rocket cannot do it. A particle cannot do it. A signal cannot do it. Locally, meaning in any small patch of space, measured against the space right there, light sets the absolute speed limit, and everything with mass falls short of it. Notice the words I keep emphasizing. Through space, locally, against the nearby space. Those qualifiers are not decoration. They are the entire loophole, and it is not really a loophole at all. It is simply the honest, careful statement of what the law actually says. Because here is what special relativity does not say. It does not say that the distance between two far apart objects cannot grow faster than light. It does not impose a simple speed limit on the expansion of space itself across cosmological scales. Relativity governs how things move through space. It does not forbid space from stretching, and it certainly does not cap how fast the total distance across a vast stretch of expanding space can accumulate. These are different claims, and conflating them is the single most common error people make about cosmology. Motion through space is one thing. The growth of distance because new space is appearing everywhere is another thing entirely. The speed limit applies with total authority to the first. It simply does not apply in the same simple way to the second. Let me make this physical, because space stretching can sound like empty poetry until you picture it correctly. Imagine an enormous rubber sheet and glue small buttons onto it, scattered all across its surface. The buttons are galaxies. Now stretch the sheet uniformly in every direction. Every button moves away from every other button. But notice, no button is sliding across the rubber. Each button stays firmly fixed to its own patch of rubber. It is not crawling over the surface at all. The buttons separate not because they are moving across the sheet, but because the sheet between them is growing. Now here is the crucial part. Pick any one button and look at its neighbors. Nearby buttons drift away slowly, because there is only a little rubber between you and them, and only a little new rubber is being added there. But a button on the far side of the sheet recedes quickly, because there is a vast amount of rubber between you and it, and every stretch of that rubber is expanding at once. Add up all that expansion across the huge distance, and the far button races away, far faster than any nearby button, even though no button anywhere is moving across the rubber at all. This is exactly how the expanding universe behaves. Every galaxy sits, more or less, at rest in its own local patch of space. It is not rushing through space at enormous speed, but the space between us and a distant galaxy is expanding everywhere along the line between us, and the further away the galaxy, the more expanding space lies between us and it. And so, the faster the total distance grows. This is the origin of one of the foundational facts of cosmology. The farther away a galaxy is, the faster it recedes from us. Double the distance and you roughly double the recession speed, because there is twice as much stretching space in between. This relationship, recession speed rising in proportion to distance, is not a strange exception, It is the natural signature of uniformly expanding space, precisely what the rubber sheet predicts. And now you can see the resolution to the brain-breaking sentence. If recession speed grows with distance, then at some sufficiently large distance, the recession speed reaches the speed of light. And beyond that distance, it exceeds it. Galaxies past that point are receding faster than light, but not one of them is moving through its local space faster than light. Each one sits quietly in its own patch, obeying relativity perfectly, its local speed far below the cosmic limit. It is only the accumulated stretching of all the space between us and them that adds up to a faster than light separation. No law is broken because no thing is moving faster than light through space. Distance is growing faster than light, and distance growing is not the same as an object moving. The law and the paradox coexist in perfect peace once you keep those two ideas apart. That special distance, the one where the recession speed exactly equals the speed of light, has a name. It marks a boundary called the Hubble sphere, and its radius is called the Hubble radius. Inside the Hubble sphere, galaxies recede more slowly than light. Outside it, they recede faster than light. It is a real, meaningful surface, and it is deeply important. And now I have to warn you about it, because the Hubble sphere is the single most misunderstood boundary in all of cosmology. And the misunderstanding is so tempting that even careful people fall for it. Here is the trap. It is desperately natural to assume that the Hubble sphere is the edge of the observable universe. That the point where galaxies start receding faster than light must be the point beyond which we can no longer see them. It feels like it has to be true. If a galaxy is running away faster than light can travel, then surely its light can never catch up to us. And surely everything beyond the Hubble sphere is invisible, cut off, gone. It is a beautiful, clean, intuitive picture. And it is wrong. The Hubble sphere is not the edge of the observable universe. It is not a permanent wall that light cannot cross. Galaxies well beyond the Hubble sphere. Galaxies receding from us faster than light right now are visible in our telescopes tonight, their light arriving as we speak. This is not a contradiction. It is one of the most beautiful subtleties in the whole subject, and I want to walk you through exactly why it happens. Because once you see it, you will never again mistake the Hubble sphere for the edge of anything. The mistake comes from imagining the situation as frozen. If the expansion rate and every galaxy's distance stayed fixed forever, then yes, a galaxy receding faster than light would have light that could never reach us. Its light would set out toward us, but the space between would grow faster than the light could cross it, and the light would forever lose ground, carried away from us faster than it could approach. In a frozen, unchanging universe, the Hubble sphere would indeed be a wall. But the universe is not frozen. The expansion rate changes over cosmic time. The distances change, and the position of the Hubble sphere itself changes. And it is precisely this changing, this refusal of everything to hold still, that lets light from beyond the Hubble sphere reach us anyway. Follow a single beam of light on its journey, and you will see the whole miracle unfold. Long ago, a distant galaxy, one that was, at the time, receding from us faster than light, emitted a beam of light toward us. At the moment of emission, that light was in a region where space was expanding away from us, faster than the light could travel toward us. So at first, incredibly, the light was actually getting farther from us, not closer. Picture it. The light is trying to swim upstream toward us, but the current of expanding space is sweeping outward faster than the light can swim. So the light is carried backward, its distance from us increasing even as it points our way. It seems doomed. It seems like it can never arrive. But the beam is not stuck in one place. It is traveling, always moving through space toward us, always crossing into new regions. And as it crosses region after region, and as cosmic time passes, two things change in its favor. The expansion rate of the universe evolves, and the Hubble sphere itself shifts outward, engulfing more territory. Over the aeons, the light gradually crosses from a region where space was receding from us faster than light into a region where space recedes more slowly. It passes across the Hubble sphere from the outside in. And once the light finds itself in a region where the local space recedes more slowly than light travels, it begins, at last, to make real progress toward us. The current is no longer overwhelming. The light starts closing the gap, and eventually, after a journey of billions of years, it arrives. We catch it. We see the galaxy, a galaxy that was receding faster than light when it sent that beam, a galaxy that may still be receding faster than light right now, in the present. Its ancient light reached us anyway, because the Hubble sphere is not a fixed wall, but a shifting, breathing boundary, and light can cross it. So please, carry this correction with you and never let it go. Say it plainly. Faster than light recession does not automatically make a galaxy invisible. This is worth dwelling on as its own distinct fact, because the wrong version is so widespread, it has become a kind of folklore. The idea that the moment a galaxy's recession crosses the speed of light, it must wink out of view, cut off from us forever. It is simply not so, and the error is not a small one. A very large share of the galaxies we routinely photograph, study, catalogue, and marvel at are, at this very moment, receding from us faster than light. And there they are, plainly visible in our images, their light having threaded its way across the moving Hubble sphere over the long ages of its journey. If you took the rule, faster than light means invisible, seriously, you would have to throw out a great swath of everything astronomers have ever observed of the distant universe. The distant galaxies in our deepest images are overwhelmingly, superluminally receding galaxies whose light nonetheless got here. So the correct statement has two halves, and you must hold both. Recession speed can exceed the speed of light, and light from such galaxies can still reach us. Neither half cancels the other. The Hubble radius is a genuine and important marker. It divides galaxies whose recession is slower than light from those whose recession is faster, and that distinction matters for the physics. But it is emphatically not the edge of what we can see, and it is not a barrier light can never cross. It is a permeable, moving surface, and treating it as a solid wall is one of the deepest and most common misconceptions in the entire field. Now, if you are following closely, you may sense a new tension building, and you should, because it is the tension that leads us to the heart of everything. I have just told you two things that seem to pull against each other. First, that light from beyond the Hubble sphere can still reach us, because the Hubble sphere shifts over time and light can cross it. That sounds hopeful. It sounds like nothing is truly out of reach, like the universe is generous. But second, a little while ago, I insisted that there is a cosmic event horizon, a limit beyond which our own signals can never reach, doors that are permanently closing. How can both be true? How can light cross the Hubble sphere freely, and yet there be a hard limit on what we can ever reach? The resolution to that tension is the whole point, And to reach it, we have to introduce the one ingredient we've been holding back. The ingredient that turns a merely expanding universe into a universe of closing doors. That ingredient is the acceleration of the expansion. And behind the acceleration lies something we call dark energy. I'm going to explain dark energy only as far as we need it, and no further, because it is easy to fall down that particular well and never climb out. And our story tonight is not really about dark energy for its own sake. Here is the essential fact, and I want to walk into it slowly, because the crucial thing is not just that the expansion accelerates, but why acceleration, as opposed to mere expansion, is what manufactures a permanent horizon. For most of cosmic history, the expansion of the universe was slowing down. Sit with why that is, because it is the intuitive part, the part that makes sense. The universe is full of matter, galaxies, gas, dark matter, all of it. And matter gravitates. Every scrap of matter pulls on every other scrap. And all that mutual gravitational pull, summed across the whole cosmos, acts as a brake on the expansion. Space flings the galaxies apart. Gravity tries to haul them back together. And so, for billions of years, the expansion coasted along but steadily lost speed, decelerating under the collective gravity of everything in it, exactly as a ball thrown upward slows as Earth's gravity tugs it back. In a universe like that, expanding but decelerating, the reach of our future signals actually keeps growing, because as the expansion slows, light finds it easier and easier to make headway against a gentler and gentler current. Such a universe has no permanent event horizon. Given enough time, a signal can eventually get almost anywhere. But when astronomers carefully measured the expansion history, tracking how fast distant regions were receding at different epochs, they found something no one was looking for and almost no one expected. Several billion years ago, the deceleration stopped, the braking gave way, and the expansion began instead to speed up. It is now accelerating. The galaxies are not merely receding, they are receding at an ever-increasing rate, the distances between them opening faster and faster with every passing epoch. The ball thrown upward didn't fall back. Partway up, as if seized by some strange new push, it began to rise faster. Something is driving that acceleration. Some property of the universe that pushes the expansion to quicken rather than slow, overpowering the gravitational brake of all the matter there is. We call it dark energy, and I will be honest that the name is mostly a label for our ignorance. It marks the thing responsible for the acceleration without claiming to fully understand its nature. But I want to be extremely careful about what dark energy is not, because there is a seductive and wrong picture of it. Dark energy is not a conventional force blowing individual galaxies through space like wind pushing leaves. It does not grab galaxies and shove them across the cosmos. Galaxies are still essentially sitting at rest in their local patches of space, just as they always were, each one riding its own patch of the stretching sheet. What dark energy does is affect the stretching of space itself, causing that stretching to accelerate. It is a property woven into space that makes the expansion of distance speed up over time. The galaxies are not being pushed through space, the space between them is being made to grow ever faster. Keep that distinction sharp. It is the same distinction between motion through space and the growth of space that saved us from breaking relativity, and it saves us again here. Dark energy is not a wind. It is an acceleration of the stretching. And now, at last, We can resolve the tension, and in resolving it, we arrive at the deepest truth of our cosmic situation. Here is the precise reason acceleration changes everything. In a universe whose expansion is merely coasting or slowing, the Hubble sphere grows over time, sweeping outward and engulfing ever more territory, and light from more and more distant galaxies can eventually cross into the slower receding region and reach us. Such a universe is generous. The current everywhere is easing, so light keeps gaining ground. Given enough time, its light finds its way home from almost anywhere. But in a universe whose expansion is accelerating, our universe, the story inverts. The Hubble sphere does not run away outward forever. The acceleration means distant regions recede faster and faster as time goes on, so that a signal setting out now toward a far target faces a current that does not ease but strengthens ahead of it. And this manufactures something a merely expanding universe simply does not have: a cosmic event horizon. A distance beyond which, no matter how much time passes, no matter how long we wait, a signal we send today can never arrive. The acceleration is not a detail, it is the very thing that closes the doors. A decelerating universe leaves them open. An accelerating universe swings them shut. That is why dark energy sits at the center of this whole story. Think again about that beam of light we followed across the shifting Hubble sphere. But now imagine trying to send a beam of our own outward from us to a distant galaxy in an accelerating universe. Our beam sets out toward the galaxy at the speed of light. But the space between us and the galaxy is not just expanding, it is expanding at an accelerating rate, opening faster and faster as our beam travels. For a nearby galaxy, our beam can win the race. It crosses the intervening space before that space can grow beyond its reach. But for a sufficiently distant galaxy, the accelerating expansion adds distance faster than our beam can ever close it. And it adds distance faster and faster forever. So the beam falls hopelessly, permanently behind. It never arrives. Not in a billion years. Not in a trillion. Not ever. The galaxy sits beyond our cosmic event horizon. We can see its ancient light it sent long ago, which crossed to us while the doors were still open. But a message we send today will never reach it. We can watch it. We cannot touch it. The door between us has shut and the acceleration has bolted it forever. This is why the earlier tension dissolves. And it dissolves cleanly once you notice that the two facts are about opposite directions in time. Light from beyond the Hubble sphere can indeed still reach us, but that incoming light was emitted long ago and threaded its way across the shifting boundary while conditions still allowed. That is entirely about the past, about light already in transit finding its way home to us. The event horizon, by contrast, is entirely about the future, about whether a signal launched now from here can ever get out to there. And in an accelerating universe, those two questions have genuinely different answers. Old, already traveling light can still arrive from remarkably far away, because it has been journeying toward us the whole time. New signals, only now setting out, cannot reach nearly as far, because the accelerating expansion will outrun them before they arrive. The Hubble sphere is permeable to light that has been traveling toward us for aeons. The event horizon is an absolute limit on the future reach of anything we send today. They are different boundaries answering different questions. Incoming past versus outgoing future. And is the acceleration, dark energy's signature, that pries them apart and makes the event horizon a permanent wall against our outgoing signals, even as incoming ancient light keeps flooding in. Let me gather the three boundaries together now, side by side, because keeping them distinct is the hardest and most important intellectual task in this entire subject, and people muddle them constantly. There is the particle horizon, the edge of what we can see, the reach of all the light that has had time to arrive, growing outward year by year as ancient light completes its journey. There is the Hubble sphere, the surface where recession speed equals the speed of light, dividing slower than light recession inside from faster than light recession outside. A real and shifting boundary, but not a wall, and not the edge of the visible universe, since light crosses it freely over cosmic time. And there is the cosmic event horizon, the limit on what we can ever reach or influence, the distance beyond which any signal we send today will never arrive. A genuine and permanent barrier to our future reach, created by the accelerating expansion. Three boundaries, three different meanings. One looks back at the light of the past. One marks where recession outpaces light. One looks forward and counts the doors that have closed. Confuse any two of them and the cosmos becomes incoherent. Hold all three apart and it becomes luminously clear. And notice what the acceleration has done to the shape of our situation, because it is quietly devastating. The particle horizon is growing. We can see more and more with each passing year. But the event horizon means the reachable universe is not growing in the same way. If anything, in the accelerating future, the region we can ever hope to touch is shrinking relative to what we can see. More becomes visible, less becomes reachable. The universe opens itself to our eyes even as it closes itself to our hands. We are being granted an ever larger view of a cosmos that is, at the same time, placing ever more of itself permanently beyond our grasp. That is the strange and poignant asymmetry that the acceleration of expansion carves into our future. And it is the exact opposite of what intuition expects. Which brings us to the question we've been circling from the very beginning, the one we can finally confront head on. We have established that galaxies can recede faster than light, without breaking any law. We have established that their ancient light can still reach us across the shifting Hubble sphere. And we have established that the accelerating expansion has drawn a cosmic event horizon around us, a limit on what any signal of ours can ever reach. So now we must ask the hard, concrete question. Of all the galaxies blazing in our night sky tonight, all those visible points of ancient light, how many could we actually reach? Not see, reach. If we launched a signal today or dreamed of a ship, how much of that glittering, visible cosmos lies within our future grasp, and how much of it is like a beautiful photograph of someone already gone, present to our eyes, but forever beyond our touch? The answer is going to be smaller and stranger and more humbling than you expect. And it forces us to pull apart four ideas that sound identical, but are not. What is visible? What can still send us light? What could receive a signal from us? And what a traveler could ever physically reach? Those four are not the same region. And the gaps between them are where the true scale of our reach and the true scale of our isolation finally comes into focus. So let us ask the hard question directly, the one everything has been building toward. Of all the galaxies shining in the sky tonight, how many could we ever actually reach? And to answer it honestly, we have to do something that sounds pedantic, but is in fact the key that unlocks the whole mystery. We have to separate four ideas that people treat as one, but which are, in an accelerating universe, four genuinely different regions of the cosmos. Let me name them plainly. First, what is visible to us now? Second, what can still send light? that will eventually reach us in the future? Third, what could receive a signal we send from Earth today? And fourth, what a spacecraft, traveling below the speed of light, could ever physically arrive at? 4 categories. They sound like they should describe the same set of galaxies. They do not. And the gaps between them are where the true shape of our situation lives. Start with the first, because it is the largest and the most familiar. What is visible now is the entire observable universe. That bubble of arrived light, roughly 46 billion light years in radius, 93 billion across, filled with something like 2 trillion galaxies. Every one of those galaxies is visible in the sense that its light, or light from its region, has reached us. This is the grand, glittering catalogue of everything we can see. And here is the first thing you must never forget as we go. Being in this category, being visible, tells you almost nothing about whether a galaxy is reachable. Visibility is about light that has already arrived. Light that's set out long ago when the doors were still open. A galaxy can be blazing in our finest telescopes, and yet be, in every meaningful sense, gone from our future forever. The photograph is bright. The subject may be unreachable. Now the second category, galaxies that can still send us light, we will eventually receive. This is subtly different from the first. The first category is about light that has already arrived. The second is about whether future light a galaxy emits from here on out, will ever make it to us. And in an accelerating universe, these two are not the same. There are galaxies we can see right now, by their ancient light, whose newer light will never reach us. Think carefully about what that means. We see such a galaxy as it was billions of years ago, because that old light got here. But the galaxy has kept living in the time since. It has kept forming stars, kept turning, kept changing, and the light it emits in its present state, the light carrying the news of what it looks like now, is caught in space that is expanding away from us too fast for that light to ever complete the trip. So we will keep seeing the galaxy, but always as it was in the deep past. Its ancient light continuing to trickle in, ever more stretched and dimmed. We will never see it age past a certain point. Its present and its entire future are sealed off from us. The light already in transit will keep arriving for ages, but no new bulletin from that galaxy's later life will ever be delivered. We are watching a broadcast that was cut off long ago, whose final frames are still crawling toward us, and will never show us anything past the moment the signal was severed. This is one of the most haunting facts in all of cosmology, and it deserves to be said slowly. For a great many of the galaxies we can see, we are seeing light from a past that we can never get an update on. Their present condition, what they actually look like at this cosmic moment, cannot be observed by us, not now and not ever, because the light carrying that present is being outrun by the expansion. We do not see those galaxies as they are. We see them as they were, frozen at the last moment. Their light could still escape toward us. Everything they have done since is, to us, permanently unknowable, not hard to observe, not faint, unknowable, cut off by the accelerating growth of the space between us. And this is not some rare, exotic subset of the sky. It is most of it. The overwhelming majority of the 2 trillion galaxies in our images fall into exactly this condition, visible only as ancient information, their present states already sealed away. When you look at a deep image of the distant universe, You are looking almost entirely at a museum of the past, hung with portraits of galaxies whose living, present-day selves you will never lay eyes on. And that observation forces a strange and profound realization about the word now. We casually assume there is a single, universal present moment ticking across the whole universe, the same now everywhere. So that we could, in principle, ask, what is that galaxy doing right now? And expect the question to have a meaningful, observable answer. But there is no universal present moment that can be observed instantaneously across cosmic distances. There is no cosmic clock we can all read at once. Every piece of information about a distant place is old by the time it reaches us, older the farther away the place is, and for the most distant regions the delay is so vast and the expansion so relentless that there now is a place we can never receive any signal from. Now, across the universe, is not a shared instant we can witness. It is a horizon of the imagination. We can define it in our models, in our mathematics. We simply cannot ever see it. And this points at something so fundamental about astronomy that it changes what the whole enterprise even is. Astronomy is, always and unavoidably, the study of the past. Every telescope is a time machine and it only points one way, backward. When you look at the moon, you look 1¼ seconds into the past. When you look at the sun, 8 minutes. When you look at the nearest star, 4 years. And when you look at a distant galaxy, you look millions or billions of years into the past, with no exception and no escape, because the light you are catching is the only news you will ever get, and that news is always old. There is no dial you can turn to see a distant object as it is at this instant. To see it at all is to see it as it was. The farther out you look, the deeper into the past you peer. Distance and look back time are not two separate measurements that happen to correlate. They are welded into a single thing by the finite speed of light. Greater distance simply is greater age. The map of the sky is a map of history, with the recent past close at hand, and the ancient past far away, and the deepest reaches of that map showing us the infant universe itself. No astronomer has ever seen the present state of anything beyond arm's reach. We are all, always, historians of the sky, reading light that was written long before it arrived. And no telescope that will ever be built can change this, because the limit is not in the instrument. It is in the nature of light and time themselves. Now the third category, and here the ground shifts under us again. Galaxies that could receive a signal we send from Earth today. We have already met this boundary. It is the cosmic event horizon, the limit imposed by the accelerating expansion on how far any outgoing signal of ours can ever travel. And this region is dramatically smaller than the region we can see. Let that sink in against everything we just said. There are galaxies we can see. There are galaxies whose ancient light still reaches us. And then there is a much smaller inner region, the galaxies that could actually receive a message we transmit right now. A signal we send today, moving at the speed of light, will reach the galaxies inside our event horizon and will never reach the ones beyond it, because the accelerating expansion adds distance to those farther galaxies faster than our signal can ever close the gap. So most of the 2 trillion galaxies we can see are galaxies we could never talk to, never signal, never influence in any way, starting from this moment. We can see them. We cannot reach them, not even with light, not even with infinite patience. The doors between us and the overwhelming majority of the visible cosmos have already closed. And then the fourth category, the smallest and most sobering of all, galaxies a spacecraft could ever physically reach, traveling, as any real spacecraft must, below the speed of light. If a signal moving at light speed can only reach the galaxies inside the event horizon, then a ship moving slower than light can reach fewer still. A smaller region nested inside the region light can reach. Because here is a truth that our science fiction dreams tend to paper over. Even some regions that light could theoretically reach would remain impossibly, permanently distant for any plausible spacecraft. It is tempting to imagine that if we could just build a fast enough ship, one that flies at 90%, 99%, 99.9% of light speed, we could go anywhere the light goes. But that is not how it works in an expanding universe, and the reason cuts to the very heart of this whole story. And I want to be concrete about why the ship reachable region is smaller than the signal reachable one, because it is not a mere technicality. A signal of light travels at the absolute maximum speed the universe permits. It is the fastest possible messenger, the very thing that defines the event horizon. A spacecraft, by contrast, must always fall short of that speed. It carries mass, and mass can only ever approach the speed of light, never reach it, and in any realistic scenario falls very far short indeed. So in the race against the accelerating expansion, a ship starts with a permanent handicap that light does not have. Every target that light can only just barely reach, arriving after an eternity of struggle against the swelling space, is a target a slower ship arrives at never, because the ship is always losing that same race by a wider margin. The event horizon marks the farthest that a perfect light speed signal can go. A real traveler, moving below light speed, is bounded by something tighter still, an inner frontier nested inside the signal horizon. So there are galaxies we could send a beam of light to, in principle, that no ship could ever physically visit, because the beam wins the race by a hair, and the ship, forever slower, loses it. The region we could ever actually go to, in the flesh, in a vessel, is the smallest region of all. The reason underneath all of this is that expansion is not something you can outrun by going faster within local space. Recall the deepest lesson we have learned. The distance to a faraway galaxy grows not because the galaxy is moving through space, but because new space is opening up everywhere between here and there, and in an accelerating universe, opening faster and faster. A traveler moving through local space, even at nearly the speed of light, is still just moving through local space. They cannot cross the intervening distance faster than light does. And if light itself cannot win the race against the accelerating expansion to a given galaxy, then a slower traveler certainly cannot. Traveling faster within your local patch of space does not automatically overcome cosmic expansion, because the expansion is not a headwind you can power through. It is the road itself lengthening beneath you, everywhere at once, faster and faster. You can be the swiftest thing imaginable in your own neighborhood, and still watch your destination recede from you faster than you can approach it. Because the space between you is being created faster than you can eat it up. The expansion can carry a destination away faster than any traveler can close the distance. Speed within space is simply the wrong tool for the problem. The problem is the growth of space, and no amount of local velocity solves it. So we must abandon, gently but firmly, one of the most cherished fantasies of space exploration. The idea that humanity could someday reach the edge of the visible universe, if only we built a ship fast enough, one that flew close to the speed of light. We could not. Even a ship at the very brink of light speed is bounded by the event horizon at best, and in practice by something tighter, and the great majority of the galaxies we can see lie hopelessly beyond even that. The visible universe is not a territory awaiting a fast enough explorer. Most of it is a vast archive of arrived light, depicting places no traveller from Earth could ever set foot upon, no matter their speed, no matter their patience, no matter how many billions of years they were willing to spend. The stars in those images set their light loose long ago. The space between raced open behind it, and no ship, however swift, can cross a gap that grows faster than it can be crossed. This naturally raises the question everyone wants answered with a single clean number. So what fraction of the observable universe is reachable? And here I have to be careful and honest rather than tidy, because the honest answer resists a single clean number. You will sometimes hear figures quoted that only a few % of the currently observable universe lies within our future reach, that the reachable region contains only a small slice of the galaxies we can see. And the spirit of those figures is correct. The reachable portion is indeed a small fraction of the visible whole. But I will not hand you one exact percentage and pretend it is settled, because the precise value depends entirely on the cosmological model you assume, on the details of the expansion history, on the exact behavior of dark energy, on how the acceleration plays out over cosmic time. Change those assumptions, and the number changes. What is robust, what all the reasonable models agree on, is the qualitative truth. Only a limited portion of the currently observable universe lies inside humanity's future causal reach, and it is a small portion. The exact figure is model dependent, and honest cosmology states the assumption before it states the number. What is not in doubt is the shape of the answer. Most of what we can see, we can never reach. Now step back and hold all four categories in view at once, because seeing them nested reveals the whole architecture. The largest region is everything visible, 2 trillion galaxies, 46 billion light years out. Inside it, a smaller region, galaxies whose future light will still reach us. Inside that, smaller still, galaxies that could receive a signal we send today, the event horizon. And innermost, smallest of all, galaxies a real, sublight speed ship could ever physically reach. 4 concentric regions, each dramatically smaller than the one enclosing it, and the outermost, everything we can see, dwarfing the innermost, everything we can touch, by an enormous margin. That nesting is the answer to our question. We can see a vast cosmos. We can reach a tiny corner of it. And no technology, no speed, no patience changes the fundamental shape of that nesting, because it is carved by the expansion of space itself. Let me now show you what this means for the far future, because it turns the abstract into something almost unbearably vivid. The galaxies beyond our event horizon do not vanish suddenly. They do not blink out. They do not cross a visible wall and disappear. Instead, they fade, slowly, gradually, over immense spans of time. As the accelerating expansion carries them ever farther and faster, the light they emit is stretched to longer and longer wavelengths, dragged toward the red and beyond. The same reddening we met with the oldest light of all. Their light grows more and more red-shifted. Its wavelengths stretch toward the infinite. Its energy sapped lower and lower. And as the light stretches, the galaxies dim. They grow fainter and fainter, their images reddening and weakening, until eventually their light is stretched so far, so faint, so low in energy, that it slips below any conceivable threshold of detection. They become, at last, observationally inaccessible. Not because they crossed a boundary in space, not because they winked out, but because their light has dwindled to a whisper, too faint and too red for any instrument to catch. They recede into invisibility, not with a disappearance, but with an infinite fade. I want you to sit with how gentle and how absolute that fading is, because it is unlike anything in ordinary experience. A galaxy sliding beyond our reach does not go out like a candle. It goes more like a sound dying away, a note held so long and stretched so low that its pitch drops beneath hearing while, in some sense, it is still sounding. The galaxy is still there. Its light is still coming, but each wave of that light is longer than the one before, each crest arriving a little later, the whole signal drooping toward an endless, toneless red, until the moments between one crest and the next stretch toward eternity, and the light, for all practical purposes, simply stops arriving. There is no instant of vanishing you could point to. There is only a fading that goes on forever and completes never, an object drowning by degrees in the deepening redshift, present in principle and absent in fact. That is how the accelerating universe removes things. Not by taking them away, but by stretching the connection between us and them until it thins to nothing. Imagine an observer in the very distant future, hundreds of billions of years from now, looking out at the sky. For them, the accelerating expansion will have carried away nearly everything. All the countless galaxies that fill our sky tonight will have reddened and dimmed and faded beyond detection, one by one, until the distant universe has gone dark to them. And what will be left? Only the galaxies close enough to be held together against the expansion, the galaxies bound to us by gravity strongly enough to resist the cosmic tide. That future observer, looking out, may see only our own gravitationally bound neighborhood, the local group of galaxies, or rather what it will have become by then, surrounded by an apparently empty, endless dark. They will have no way of knowing, from direct observation, that a vast universe of 2 trillion galaxies once blazed all around. The evidence will have faded past recovery. Their observable universe will have shrunk to a single island of bound galaxies in an ocean of black. And there is something almost unbearably poignant in that thought, because it means the era we live in right now is a privileged one for knowing the truth. We happen to exist early enough in cosmic history that the far galaxies are still visible, their light still arriving, the great structure of the cosmos still spread out before us to be measured and understood. A civilization arising in that far future, in the bound remnant, looking out at nothing but dark, might construct a perfectly sensible cosmology in which their island of stars is the whole of creation, and they would have no way, from what they could see, to know they were wrong. The evidence that would correct them will have receded beyond their horizon forever. We are, in a real sense, living in the golden hour of cosmic observation, when the view is still wide and the record still legible. That the universe granted us that view and granted us minds to read it is not nothing, which raises the crucial question: what survives the expansion? What is bound tightly enough to resist being torn away? And the answer is a genuine comfort in all this cosmic loneliness. Not everything expands. This is a point people badly misunderstand, so let me be precise. The expansion of space dominates on the enormous scales between galaxies and especially between clusters of galaxies. The vast, near-empty intergalactic distances where there is little matter to hold things together. But on smaller scales, where gravity is strong, gravity wins, and the expansion does not tear those systems apart from within. The solar system is not expanding. The sun's gravity holds the planets firmly in their orbits, and has for billions of years. The Milky Way is not expanding internally. The galaxy's own gravity binds its hundreds of billions of stars into a stable wheel. The local group, our Milky Way, the Great Andromeda Galaxy, and the several dozen smaller galaxies gathered with them, is bound together strongly enough by mutual gravity to hold as a unit against the cosmic expansion. These bound systems do not stretch along with the universe the way the immense intergalactic gulfs do. They are islands of gravity's dominion, holding firm while the space between the islands races apart. And here is a beautiful and clarifying consequence of that fact, one that trips people up until they see it. If the universe is expanding, how can the Milky Way and Andromeda be approaching each other, destined to collide and merge in a few billion years? Should not the expansion be carrying them apart? The answer is that the Milky Way and Andromeda are bound to each other by gravity. They are part of the same gravitationally held local group. And within a bound system, gravity governs the motion, not the expansion. The two great galaxies are falling toward each other under their mutual gravitational pull, drawing closer despite the overall expansion of the universe, because on their scale, gravity is the stronger hand. They will meet, pass through each other, and eventually merge into a single galaxy. And the expansion of the universe as a whole will not prevent it, because bound systems do not expand internally. The cosmic tide flows between the islands, not through them. So the far future observer's sky, dark and lonely as it will be, will still contain this bound remnant. The merged descendant of the Milky Way and Andromeda and their companions, a single island of light in the encroaching black, all that remains observable of a cosmos that was once unimaginably full. Now let us gather everything and stand back to see the whole shape of the truth we have uncovered, because it is time to say plainly what all of this has been building toward. We began with a paradox. A universe 13.8 billion years old, whose visible edge lies 46 billion light years away, because space expanded while ancient light crossed it. We followed that ancient light back to the oldest glow there is. The afterglow of the moment the cosmic fog cleared, not the beginning, not an edge, but the surface where light first ran free. We separate the horizons, the particle horizon of what we can see, growing outward as more light arrives. The Hubble sphere where recession reaches light speed, permeable and shifting, not a wall. And the cosmic event horizon, the true and permanent limit on what our signals can ever reach, drawn by the accelerating expansion that dark energy drives. And finally, we pulled apart the four categories: visible, still able to send us light, able to receive our signal, physically reachable, and watch them nest inside one another, each far smaller than the last, until the region we can touch dwindled to a mere fragment of the region we can see. And notice the strange tension we are left holding, the very tension we flagged at the outset, now fully understood. The observable universe is growing. With every passing year, light that has travelled a little longer completes its journey, and new regions swim into view. Yet, at the very same time, The accelerating expansion means the region we could ever reach or influence is, in proportion, shrinking. More galaxies slipping across the event horizon into the unreachable dark, their doors closing forever even as their ancient light keeps arriving. More becomes visible, less becomes reachable. The universe opens itself ever wider to our eyes while sealing itself ever more tightly against our hands. That is not a contradiction. It is the precise and poignant signature of living in an accelerating cosmos. Which brings us at the very end to the difference between two things we too easily confuse: seeing an object and being able to interact with it. We can see nearly the whole visible cosmos, 2 trillion galaxies, their light gathered from across 46 billion light years and 13 billion years of time. But we can interact with, reach, influence, or ever hope to touch only the smallest sliver of it. The overwhelming majority of what fills our sky is ancient light from regions whose present state we can never know, and whose future we can never affect. Galaxies we are permitted to watch but forbidden to reach. Images of a past that will never take our call. The universe we can see is not the universe we can reach. They are 2 different universes, one vast and one small, nested one inside the other, and we live at the center of both. Not because we are special, but because that is simply where we happen to be looking from. And even all of that, the whole 93 billion light-year sweep of everything we can see, may itself be only a tiny portion of everything that exists. Beyond our horizon, the real universe very likely continues. More galaxies and more cosmic web, much like our own, possibly without any edge at all, possibly forever. We cannot see it. We can only reason that it is almost certainly there. So we are left holding a truth both humbling and strangely beautiful. We can see far more of the universe than we can ever reach, and even the boundless sea we can see may be the merest droplet of all there is. We are watchers of a cosmos, most of which we can never visit, gazing out from a small, bright island at an ancient, glittering, receding dark. And the watching itself, the fact that a corner of that cosmos woke up and understood its own reach and its own limits, may be the rarest and most precious thing in all of it.